Okay, and we're off. So we are entering our 5th week here, and exam 1 is not next week, but I thought I'd just get you ready or begin to get you ready. So you've learned some of the system, how we're doing things. And now in week 9, we're going to release exam 1. And I'll go over the details here in a second. So as exam 1 gets closer, I'll talk to you more about, what I'd like to do and what I intend to do. And exam 1 and exam 2 are probably going to be run pretty much the same. Exam 2 is in week 16, the last week of the course. And we'll see how things go in this first exam, if we have to make any adjustments. Let me move the paper up slightly. So, and if you have any questions you want to work on today or ask about homework I returned or anything like that, just alert me and we'll put it over here in the question window. I returned your written homework number 2 to you in the folder that I'm sharing with you, and I returned a grade report to you. Bring in a couple more people as we go along. So now you have the graded homework number 2, and you have your grade report counting your XYZ homework and your homework number 2 to date. Make sure you're submitting those homeworks. So you can say the written homework's only worth 10%, but if you don't submit it, you're just tossing 10% away. So it's not a great idea. And further, the written homework is practice for writing things for the exam. So you definitely want that practice. What else do I want to say about that? Make sure, as we said earlier, that you read the grade report and you make sure that I have your numbers entered correctly from the XYZ homework and from, let a couple more people in, and from the written homework. So, and remember that you have a second, the next written homework due tomorrow night. So just pop over to my website for just a second. And I gotta see where we are. Okay, good. So here we're on our week 5 page, sharing the week 5 page with you. And under homework, here's your next written homework, homework number 3, due tomorrow night. And today sometime I'll release homework number 4. I'll come back to this webpage in a second. I think I have to always remember, I may not have started that way, admit another person. I always have to remember to focus the camera on the paper that we're writing here. So this is kind of the format we're going to use for the first exam. Just format. Now we'll get into more like what questions are and things like that later. But you have some homework that'll be due on Tuesday, October 27th at 11:59. So that'll be your ordinary homework, a written homework and XYZ homework. So at that time, I will release the first exam Tuesday, maybe a little bit before 11:59. And I'll give you 48 hours to work on it. Thursday, 11:59 p.m. And you're going to submit it to our assignments folder just like you submit your written homework. Now, submit it as a single PDF document, and please follow our naming convention just to make sure we don't lose any papers. Last name, first name, instead of homework number, now it's exam number 1, and Math 121, and depending on what section you're in, FA 810 or FA 830. You can find that on your schedule, or I can help you find that if you're unsure. So the exam's going to be released on our website and returned to the assignments folder on our website. Make sure you submit it as a single PDF document. And I don't know how many pages I have on there because I want to provide pages and room for you to work. So just submit all the pages of the exam, including title page, as that one document. And there's the case that you don't have a printer or don't have access to a printer or don't have a way to print something. You're going to have to copy the exam neatly by hand. And the problems aren't going to be so long that you have to copy a paragraph out of a book, but you definitely have to tell me what problem you're doing and what's involved in the problem you're doing. And the title page will have several bullets on it, and I will have you copy the title page and sign it. Remember that all the graphs you draw, whether they're on homework or exam, you should draw them on graph paper. And graphs that are not drawn on graph paper are going to be kind of rough and not quite accurate. And we need to graph and grade for accuracy. So you have graph paper that you can print off my website. If you can't print it, you can go to Walmart, Office Max, Staples, whatever's handy, and buy a pad of graph paper. But that's definitely going to improve the graphs you draw. And we're going to have to draw some very accurate graphs relatively soon. So I can expect that there might be some drawing of graphs on the exam. Okay, now that's just the format of the exam. We'll talk more about the problems as we go on, as we approach week 9. But do you have any question about the format here? Excellent question, Austin. I want to wait for a second because I'm not sure. I'll tell you this, that whenever I count problems, I don't, if there are 5 problems, but each problem has 4 parts, that's called 20 problems to me. So I haven't exactly calculated problems parts. I know in my mind that I do not want it to be a lot of questions. So then you're going to ask, well, what's a lot of questions? If I was in the classroom doing the exam with you, I would see, it could be 17, 18, 19, 20, somewhere in that area of around 20 questions. And remember, by that I mean counting all parts. And I think I want it to be less because just the format of how we're doing things, even in your grade, you realize that the exam is not the majority of your grade. If I was in the classroom again with you, I would be saying that the exams would add up to 70, maybe 80% of your grade. And here we have 2 exams that add up to 40% of your grade. So I'm not emphasizing the exams as much as I might do that in a regular classroom. So I will tell you how many questions are on the exam, but I've got to write it first. I just say less than I normally do. And I normally would give 18 to 20 questions on an exam of this type. So I can't tell you whether that means 8 to 10 or 1 more or 1 less. I will consider it carefully. I don't want it to be long. When we get closer, I'll tell you exactly how many, if that's okay. But that's a very natural and good question. Other question you'd like to ask? Is there any other question you'd like to ask? Okay. Let me show you where we're going to go this week. And let me show you a revamped formula sheet I'm working on for you. So what we open up with this week, time limit, 48 hours. So no, perfect question. I'm going to release it by midnight on Tuesday. And by that time, you've handed in your homework, so you don't have any other work for me to do. So then you have 48 hours to do the test. In a classroom, you'd have 90 minutes or 2 hours. But I understand you have other things to do besides being on a test. So I want to compromise. I'm not going to say, but I know people are doing this. And that's okay. I'm not going to say, okay, everybody log in at noon and test is done at 2, because that doesn't make much sense to me. But just 48 hours, so tight, relatively tight, not like your homework where you have a week to work on it. Okay. We'll come back and we'll talk about that and remind you more again. Very good question. Okay, let's talk about something else we need to do to calculate trigonometric functions of angles. So far, we've exclusively used the word degrees, which is absolutely fine and complete for many, many practical things. In fact, in the recent sections, you saw that if someone needed to be super exact and they chopped degrees up into 60 little pieces and call them minutes. So they have degrees and minutes, and then they chop them up into 60, each minute into 60 pieces, and call each of those pieces seconds. So in a surveying application or something like that, it's not just degrees. They're usually very, very accurate. They might measure things in degrees, minutes, and seconds. In which case they write, something like 37 degrees, 52 minutes, and 37 seconds. And each minute is 1/60th of a degree, tiny, and each second is 1/60th of a minute, which is tiny, tiny part of tiny. So in very special applications, science, surveying, engineering kind of things, you frequently hear people talk in degrees, minutes, seconds. So as far as accuracy is concerned, we can be as accurate as we want to. But there's another type of work that we have to do that degrees is not awesome for. And that's specifically graphing and future calculations. Oops, excuse me, let me let somebody in the room. So there are some cases in graphing and future calculations, the degrees, even if they can be as precise as we want, are not convenient. And so there's another way we'll measure angles called radians. Kind of sounds like a science fiction movie or something. But radians is another way we measure angles. And your calculator does both of them with ease. The major problem you got to make sure you're doing if you're doing your calculator is to know whether your calculator is talking radians or degrees at any one moment. And I'll show you where to do that. So there's a concept called radian measure that we'll talk about today. And then, I'm sorry, I wrote a little small. I'm trying to write bigger every time. And I just get trapped in thinking that I'm writing on a piece of paper instead of writing in front of a camera. Once you learn what radians are, then the first natural thing is to, well, how many degrees is that? Or if someone give you degrees, how many radians is that? So you want to go back and forth. So you want to convert from radians to degrees and degrees to radians. And that's not hard to do, with or without your calculator. Then, next thing today, we have a list of our famous triangles, or famous angles. 45, 45, 90, 30, 60, 90, 15, 75, 90. Then the quadrantal angles, 90 degrees, well, 0 degrees, 90 degrees, 180 degrees, 270 degrees. That's the way my pen is pointing. We have a lot of famous angles. And you have the experience from your current life that you often think in degrees. But now I want you to think in radians also. So I want you to know the famous angles and the famous triangles in both radians and degrees. I have a handout that's going to help you with that. And we'll make some drawings. Then I want to make you comfortable that your calculator can do calculations for any trig function in both radians and degrees. And the number one thing that goes wrong if people have a catastrophic mistake is that their calculator's in radian mode, but they thought they were calculating in degree mode, or vice versa. So always know whether your calculator is in radian mode or degree mode. Let someone else in here, got kicked out. Okay, welcome back. You know, even if you're getting some answer that just doesn't look right to you, say, am I in degree mode? Am I in radian mode? Whichever one you need at that moment. So that's, we'll look at the calculator today. And then I don't think we're going to get to this today, but as we go on Wednesday, I have a couple more identities I want to show you. I'll show you them on a piece of paper now. I'm going to expand your formula sheet. And the next concept is the so-called even-odd identities. Let me show you the expanded formula sheet on a piece of paper. It's not published on the website yet because I'm just double checking something. So this is the current formula sheet I have published for you on the website. And it might even be better for me to show it in the browser window, but I'm just letting you scan it just to remind you that this is the one we've already provided. It's got the trigonometric functions on it. It's got the properly labeled angle on it. I had an error there previously. Make sure you have the x-axis with the x mark, the y-axis with the y mark. It's got the trigonometric functions, the so-called reciprocal functions, and the reciprocal identities. Even though you cannot read this nicely on the paper right now, in your sleep, you ought to be able to recite the reciprocal identities. Cosecant is 1 over sine. Cosine is 1 over secant. Tangent is 1 over cotangent. You need to know the reciprocal identities by heart. Sine over cosine is tangent. You need to know these quotient identities. Sine over cosine is tangent. Cosine over sine is cotangent. And even before today, we were preparing to do these calculations in radians. Let me see if there's an intelligent way I could raise this sheet so that you could read it, but I won't have it flopping around because I'm holding it in midair. Let me try this. I'm always trying, I have to invent new things here, right? How's that? I just put a couple books on my desk and then put this sheet under that. That's better. Okay, I'm going to do that from now on. Welcome someone else into the classroom. Okay. So, but then I got to remove the books to do the zoom out view, but we'll deal with it. Before today, I had calculations in radians on your formula sheet, and this is how we do the calculations and conversions, and some other things that we'll talk about next week or on Wednesday. So this has already been on your worksheet, but there's something else I wanted to add. Remember, here's the instructions for when sine and cosine, secant, cosecant, tangent, cotangent are positive or negative. That's really important. And there's the cofunctions and the cofunction identities that we talked about a week or so ago, and the Pythagorean identities, which we'll talk about more after we've explained radians. But there is one more set of identities I want to add to your sheet. And we're not going to get to it today. I pretty much don't think we're going to get to it today. And I'll have to zoom on I'll zoom out on this paper in a second. But there's the so-called even odd identities. And they go like this, that the sign of minus 30 degrees is always the same as the minus sign of 30 degrees. Or the cosine of minus 70 degrees is always the same as the cosine of 70 degrees. I can explain later why they're called the even odd identities, because they talk about the symmetry of sine and cosine. So this is another formula sheet that I'm preparing. We have not gotten into any of these fancier identities. We will soon, not this week, but it's just packed with more information. So consider your first formula sheet as the preliminary sheet. This is going to be just like it, except I've stuffed in a few more identities. So that should be available on the website by the end of the week. Okay, so this is the plan for today. This is the plan for today. I want to show you other things that you're going to find useful on the website. In particular, let's go back to my browser window. That some people asking me questions about the third homework problem. Let me open up the third homework problem there. Get rid of that. I'm going to open up that. Radian measure, unit circle. Yeah, so right now we're looking at the third homework problem, which is due tomorrow night. And I have had some reports from people like, oh, that handout is really slow to load, or oh, that page doesn't load very fast. I can't tell right now whether that's an issue with my website or it's just general crazy traffic issues because everybody is overloading, Charter, Spectrum, Xfinity, whatever you're using. So if you have serious problems downloading a handout from me, like it just spins and never stops spinning, try refreshing it or reloading it. Or if it's consistently happening, just let me know so I can try to investigate it further. Right now, I think the major problem is just general traffic and everybody accessing everything online, which is kind of funny because, of course, Charter and Xfinity and everything want to talk about how fast they are and what a great service you got. Except the service does depend on your neighbor's service. So the little pipe that comes to your house, it's got a fixed capacity, same way the water pipes that come from the city got a fixed capacity. Same way the sewer pipes that leave your house and go back, the wastewater treatment plant got a fixed capacity. And I don't think anybody really anticipated how much internet people would be using in a practical way. Okay, anyway, you got the ship traveling on a course, bearing this. Draw a diagram. How far is the ship from where it began? So we demonstrated a problem like this last time. But what I wanted to show you on my website is some handout that talks about further applications of right triangles. So that handout, if I click on it, look like this. And here I was showing you, or just introducing to you, some fancier things you can do with bearing or with heading or navigation, and then also measuring the height of something that you don't have access to. If you can't like walk up to that tree that's 2 miles away, how could you measure it? And so on and so forth. So this handout can help you. The problems in the book can help you with problems of bearing and heading because he does some demonstrations of that. So that's related to, where am I? Homework number 3 that's due tomorrow night. Other handouts that I put on here just now, and this is what part of what we're going to talk about today, the unit circle. And this is where I'm going to get trapped in the slow downloading. This handout I've had on my website for some time, but we haven't had the occasion to use it. This handout I'm trying to illustrate to you that you can take the 360 degrees. Let me bring someone back into the classroom. Very good. Let me get rid of that. Very good. Now, you know that 0 degrees is where you start measuring the positive horizontal x-axis. Then 90 degrees, 180, 270, then 360 if you come back around. But then you can chop 90 degrees into 2 pieces and call it 45. Or 45 past 90 is 135. Or 45 past 180 is 225. Then you can also have 30 degrees, 60 degrees. Half of 30 degrees is 15 degrees. So this handout after this week will make more sense to you. I was trying to bring all the information you have about the famous triangles into one picture and remind you that if you know the ratios of the 15-degree angle, well, then you know the ratios of the 255-degree angle, because 255 degrees is just 15 degrees short of 270. In other words, if you know the 15, 75, 90, 30, 60, 90, and 45, 45, 90, you can make the sine, the cosine, every 15 degrees around the circle. So I'm calling this the unit circle because I'm thinking of it as a circle of radius 1. At the bottom of this handout, I placed those 3 famous triangles. So that's one handout I want you to keep your eyes on. Now, as we go finish the rest of this week, I'm going to show you this second thing called the unit circle segments. And wrong handout. Let me get rid of that. I already showed you that. I already showed you that. See, I'm experiencing that slowness too. Let me see if I can load these a different way. Unit circle segments, unit circle and circular functions, and then radian measure. Okay. I want to show them to you in order. So I'm going to just be patient for a second. Until I run out of patience and pull it up on my computer. Okay, there it is. It showed up. I also have the handouts on my computer, so I like clicking just to show you where things are. But I can also just bring them up on my screen. This is a funny looking drawing. In this funny looking drawing, you see a quarter of a circle, and then you see a vertical line that's tangent to the circle at 1, 0, a horizontal line that's tangent to, just touching the circle at 0, 1. And those things make 3 triangles. This is kind of a drawing puzzle in a way, but you see 3 triangles here. Here's a triangle. Let me blow it up. There's a triangle POQ right here, small inner triangle with angle theta. There's a triangle UOR, slightly larger, but still with this first angle theta. So POQ and UOR are similar triangles, same side ratios. And then you have this larger triangle that's upside down on top of them. This is the triangle SOV. People traditionally use O for origin, or the center of the circle. SOV. Now that does not have theta right here, but it does have theta up here at angle V, because the theta here matches the angle at V, because I have two parallel lines cut by this line segment from O to V. So I have on this piece of paper 3 triangles. It takes you a second to see them. They are all similar because they all have one 90-degree angle, one angle labeled theta, and then the complementary angle, which would be 90 minus theta at P or at U, or 90 minus theta here at SOV. I don't say 90 minus theta at the origin because the origin, the point O, has 2 angles at it, so I got to be specific. At the angle SOV, I have the angle 90 minus theta. So these 3 similar triangles demonstrate all 6 trig functions and do not obsess about all the lines and the letters right now. I'm just going to show you later how each one of these line segments is one of the trig functions. For example, the line segment sine theta is from Q to P. The height of this small triangle from Q to P is always reading the sine of theta. The cosine of theta is the line segment length from O to Q on a unit circle. The tangent of theta is the line segment length from U to R, or from R to U on the circle. And for example, the secant of theta is the line segment from O to U. Now, I have to explain why that's true, and that's not what we're going to do today, but I'm just kind of prep you for that. That you can think of the 6 trig functions as lengths of line segments in a drawing. The other thing that's handy about this drawing is that those 3 triangles, the 3 right triangles, represent the 3 Pythagorean theorems. And I could expand this window slightly. So the tiny triangle, if you'll read the sides, will say sine squared plus cosine squared equals 1. The medium triangle, which is using this rightmost vertical segment, that I colored blue here, if you can see the blue, is representing tangent squared plus 1 equals secant squared. And the upside down triangle, which is still similar to the other 2, I've colored red here. It's got the long leg on this horizontal, this upper horizontal segment. That represents 1 plus cotangent squared equals cosecant squared. So this handout is another example of how to see the 6 trig functions and see the Pythagorean identities. Okay, out of there. Now what we're going to do right now is go and explain what radian measure is. And if you want a short 1-page handout of what radian measure is, this is on our website under the handouts. And then later, when we want to explain what even odd means, or when I want to explain how to use your calculator to find some values, I have another handout here about the unit circle and the circular functions. Okay. That's some kind of long prep, but prepping like that at least tells you where we're going. So let's go back to our paper and let's talk about radian measure. Okay, I'm going to move this paper out of my way. number it. Move this out of my way and bring in this high-tech drawing device, which is just the lid off some oatmeal jar. Okay, lid off Quaker Oats oatmeal jar, because I am terrible at drawing circles. And so if you want to draw a really nice circle, what you could do is just get yourself a large can or something like that, right? So let me center this nicely on my piece of paper. I'm trying to line it up so that it kind of matches the grid lines there. And then I'm just going to draw a perfect circle. Well, as perfect as this lid is. So if you're always annoyed, like someone asks you to draw a circle and you just cannot draw a circle beautifully round, just get a large can lid. Just get a large can or Tupperware lid, something like that. Okay, now I got something that's just about a perfect circle. I'm going to draw the axes in here. And the reason I'm making this diagram, and you can make a similar diagram for yourself, is just to label it correctly with degrees and radians. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 26. So 1, 2, 3, 4, 5, 6, 7, 8, 12, 13. Not so easy to say where the center of that circle is, right? It's so big. You're not sure if you have the center in the right place. Okay, so let's start labeling. Positive horizontal axis, 0 degrees. And if I make one full trip around, 360 degrees. Of course, if I make another trip around, it'd be 720, which I don't have room to write everything I want. So I'm going to leave it there. If I went around clockwise, it would represent minus 360 degrees. But they're all landing on that line. That's called the coterminal angles. Then halfway around, of course, that would be 180. Or 540, or minus 180. I'm not going to write extra numbers here. Halfway to 180 is 90 degrees. And halfway home from 180 to 360 is 270 degrees. And then we add in all the other degree measurement angles. Now, I'll do that later, maybe, but that's what that unit circle handout is for. That's got the lines at every 15 degrees. So you can print that or copy it as many times as you want and scribble all over it. But degrees, you know, the major part of what degrees is not great for is the fact that we measure 360 degrees as a whole circle. You know, we're used to measuring, counting on base 10. So to say 360 degrees is a full circle, that makes some kind of historical sense, but it doesn't always do well for calculating. So there's another measurement of the circle that's based on its radius. So let's take the radius right here, and let's call that radius r. So it's a circle of radius r, and we can have any radius we please, of course, and I can name this any radius I please, but I'm just saying generic circle. And let's pretend this radius, this blue line that I've just drawn, is like a rope. And I can pick up the rope and place it along the outside of the circle. It's not a very long rope. So as I place it here, it's not going to go very far. I'm trying to think about what I could do to show you, and I don't have any rope handy, but I have from Ace Hardware, the happy birthday coupon from Ace Hardware. Let me cut this off right here. I just want you to see this visually. So this is just some coupon from the newspaper. I've made it, what? As long as that radius right there. So now I'm going to take this card and place it along the outside of the circle and see how far it goes and then mark where it stops. Now I can't hold it and mark at the same time. So I'm going to get an eye on where it stops. It stopped about right there. So this length of circle arc, part of a circle is called an arc. This length of circle arc is also r units long. If this is 10 feet, this is 10 feet. If this is 1 inch, this is 1 inch. And you see that with that radius and this arc length of 1r, I've drawn an angle. So now, next thing I'm looking for is a ruler to make this neat. And I'm going to mark off that angle, which, by the way, just uses another radius right here. So I can label that R if I like. And what have I drawn? I have not drawn a triangle. I've drawn a piece of pie, piece of pizza. I've drawn, in the fancy language, a sector. The math language, people call that a sector of a circle. Now, I want to be very clear that I have not drawn a triangle, even though I have something that kind of looks like a triangle, but this third side is not a straight line. And so I cannot call this a triangle. If it was a triangle with 3 equal sides, I would call that an equilateral triangle. And each one of these angles then would be 60 degrees. But think of an equilateral triangle and then think that I kind of squished this thing down so that I bent the third side. In fact, this thing that I'm holding in my hand, it's called a protractor. It measures angles. I can put this right on that angle and measure exactly what that angle is. Again, I need my book situation here, which is not a bad idea. So let's practice using my book stand. It's easier than moving my camera. And do you see that that angle, if I slide it down, that angle that I've created is less than 60 degrees? Because it's like an equilateral triangle that I squished together and bent the third side. Now I'll move my books out of the way. Oh, maybe I'll keep it here for a second. So this angle right here, let's call it theta. It is not 60 degrees. It's slightly less than 60 degrees. But when you play this game of marking out a sector with 3 R's like this, radius, radius, and arc length, this angle right here, too close to the camera, is called 1 radian. It's a way of measuring angles on a circle. First of all, you say, well, that's a goofy way of measuring angles on a circle because you can't tell me how many degrees that is. It's less than 60 degrees. Is it about 56 or 57 degrees? That's not at a nice mark for reading. So that doesn't seem convenient. But it turns out for calculating, if I measure angles on a circle in radians, it turns out to be very, very practical, much better for calculation than degrees. Okay, what I'm going to do is go back to desk height. I might consider a different table height. But I want to measure again using my coupon other distances are around the circle. So if I do it again, I'm just very carefully going to mark radians. Gets me to about right here. That's what? 2 radians. Here's another R. And this will be 1 radian, 2 radian angle. I don't want this drawing to get too cluttered, but I'm going to mark the rest of the way around the circle and then draw those lines as decently as I can. I'm not saying that I'm going to be able to mark these perfectly. So right now I'm just measuring on my piece of paper, so my hand's in the way. So that kind of blocks your vision, but I'll move my hand out of the way as soon as I get all the marks done. I'm going to come back to the start, right? But I don't land back where I started. That bugs you. Say, well, you're chopping the circle up into pieces, but the pieces aren't the same. What are you going to do about that? Right now, I'm just going to take it. So let's mark the rest of these radians. Here's another radian. And goes out there. That's 3 radians. Here comes 4 radians. Every time traveling a distance r on the outside of that circle, whatever r we choose, I didn't measure the r of my oatmeal can top. Here's another radian. So now I'm up at 1, 2, 3, 4, 5 radians. Does not seem to be matching the degrees, right? The radians don't stop where the degrees stop easily. Here's 6 radians. And a little more gets me back to the start. So 300 degrees, 360 degrees is like 6 radians plus a little more. Now, I don't know what this little more here is. Is it 45? No, that doesn't, it's too small for that. Is it 30? I think it's smaller than 30. Is it 15? I think it's larger than 15. I can't necessarily think in degrees, but I can think like this. From geometry, I know this famous formula that the circumference of the circle, 1 full trip around the circle, is equal to 2 times pi times radius. Remember, pi is this very goofy number that goes on forever, never stops, never repeats. 3.14, you don't stop there. I mean, sometimes the book says, use 3.14 as an approximate value of pi. 3.1415926538 Pi is just this weird mathematical constant that goes on forever, never stops, never repeats. I don't know if you guys have ever seen something like this. Have you ever seen a sliding puzzle? A puzzle where you slide and you get the tiles in order, stuff like that. And it's a picture of a butterfly, or it's whatever picture you're supposed to get, right? So here's a sliding puzzle with the digits of pi. So if we ever get back to campus, stop by my office. I'll give you a copy of this puzzle. But on this puzzle, I put down, oh, I don't know, 2, 4, 6, 8, 10, 12, 8, 24. I got 30 digits of pi right here. So 3.14159265358979323884626433837 You don't need to know 30 digits of pi. You don't even need to know 6 digits of pi. It's already built into your calculator. But the truly weird thing here is, check this out. Do you see that 2 times pi would be about 6.2831 if I continued on with the digits? Do you see that 2 pi is 6 1/4-ish? That's a little more than a quarter. A quarter would be 0.25. Now look at these radians. I have 6 radians, and I have what left over? Is that about a quarter of a radian? No, it's bigger than that. What I'm saying right here is when I make a full circle around, I have 2 pi radians. If I start at the beginning, I have 0 radians, 1 radian, 2 radian, 3 radian, 4 radian, 5 radians, 6 radians, 6 and a little more than a quarter radians. That's called 2 pi radians. Look at the 180 degrees. Do you see that that's 3 radians? And a smaller sliver. What do you think the smaller sliver is? I bet it's, about 0.14, 0.14-ish radians. So in this circle, when I draw the radians, I see pi right here. Pi is 180 degrees around the circle. But now I want you to think pi is 1 halfway around the circle. Pi is the distance that I walk on the outside of that circle. Let's say the circle is radius 1. Well, if the radius of the circle is 1, let me erase my paper, then the circumference of the circle is 2 pi times 1, or exactly 2 pi radians. Pretend that this radius is 1 unit long, whatever unit I'm using. That means as I walk around the outside of that circle, by the time I walk to here, I've walked exactly pi steps, pi distance. If I walk the full way around, I've walked 2 pi distance. Now, first you're going to grumble and say, oh my goodness, this is ridiculous. Why should I give up degrees? But I want you now to think in terms of pi. I want you to think in terms of pizza. I want you to think in terms of slices of pizza, fractions of a pizza. And it turns out that thinking in fractions of pi can be really efficient. Now, in order to do that, I'm going to redraw this circle. Now I'll show you another trick for drawing things. Tear off this paper. I'm not going to get out my oatmeal can again. What I'm going to do, if I want to redraw it, and I already got myself a perfect circle, is I'm going to make each one of these lines a bit heavier. And, carefully, although I can't draw it perfectly, make this circle line a bit heavier. Maybe I should just go to my drawer and pull out a thick marker. And you know what I'm about to do. So I want to make a copy of this beautiful circle, since it was so nicely round. I'm just going to put it under the next sheet of paper and trace over it. That's why I need these lines to be thick. Okay, so let's try it. So this is a good trick if you want to just make a copy of a beautiful, perfect circle. And you are looking at this through the camera, but this is actually better than I expected. Even through the camera, you can see that circle there. So I'm just going to copy it. Copy the x-axis. Copy the y-axis. Copy the circle gently. It's not going to be perfect, but it's going to be good enough to suit our purposes. Have you ever heard the phrase good enough for government work? I'm not trying to insult government work or government workers. I'm just saying that that was a common kind of a slang phrase. It came from the 1950s. Good enough for government work. So take care to trace this nicely. And then, yeah, it's a little wobbly. Okay. It's a lot better than I could draw with my bare hands, that's for sure. Now I'm going to move this other paper out of my way. But now, here's the beginning of your training to think in terms of degrees and radians simultaneously. So here's 0 degrees or 0 radians. Degrees, when you think degrees, you put a little degree symbol, which is a tiny circle up in the upper right. When you think in radians, you don't put any symbol on it. In the old days, people put a capital R up here, but that's not necessary. And then you talked about 180 degrees. And then you talked about 90 degrees. And then you talked about 270 degrees. And then you talked about 360 degrees. But I want to show you it's just as convenient to think in terms of pi, because I've already said that one full trip around the circle must be 2 pi radians. So now think of a 360-degree angle also as a 2 pi radian angle. That means halfway around the circle would be half of 2 pi. Half of 2 pi is very easy to speak. Half of 360 is not easy to speak. You just got used to it, calling it 180 for you snowboarders in the audience. Someday I'll break my neck, but I enjoy being on a snowboard better than I enjoy being on skis, whatever snow we have around here. It's easy to cut 2 pi in half. You call it 1 pi. 360, cut it in half is not hard. It's 180, but you're just not used to that if you hadn't already memorized it. How do you cut 80 in 1/2? You get 90, right? Again, not super convenient, but you memorized it. How do you cut pi in half? Well, that's simple. Pi over 2. Okay, so my numbering here is going to get a little small and a little crowded. But what I'm trying to show you is, and I got to see if I can get this all in one camera at the same time. Maybe not. Maybe I should have chose a smaller can. But now let's just start cutting this circle into pieces. So for example, dead center on 90 degrees is 45 degrees, right? You know this as 45 degrees, but now I want you to know it as a fraction of pi. So this is 1 pi, half pi, and a half of a half would be pi over 4. And think of that as 1/4 of pi, literally. Here's 1/4, 2/4. 2/4 is 1/2 pi. 3/4, 4/4. 4/4 pi is 1 whole pi. Let me draw the 45-degree angle in this quadrant. Maybe you've even done this before, that's fine, but I just want you to see it. So 45 degrees past 90 is a little bit awkward to speak, isn't it? 135 degrees. I mean, you can do it. 45 plus 90 is 135. But thinking in pies is sometimes faster. 1/4 pi, 2/4 pi, 3/4 pi. So that angle is also called 3/4 pi. Pi is 4/4 pi. Let me draw one more quarter. Now I've got 5/4 pi. Now, how much is that in degrees? Let me think about that. 180 plus 45 more is 225 degrees. Not impossible, but it doesn't roll off the tongue like 5/4. 1/4, 2/4, 3/4, 4/4, 5/4. 6/4 pi would be 3 pi over 2, although that does kind of fall off the camera viewing angle. One more quarter here would be 5/4, 6/4, 3/2. This would be 7/4 of pi, or 7 pi over 4 is more common to say it, which is 45 degrees past 270, which is 315. So I'm just showing you some common angles. One more quarter would be 1, 2, 3, 4, 5, 6, 7, 8 pieces of pizza, 8 parts. Each of them is 1/4 pi. 8 times 1/4 is 2 pi. So I could call this 2 pi. I could also call it 8/4 of a pi, or 8 pi over 4. But we don't like to write things without reducing them, so we just call it 2 pi. Now watch how that just opens the door to lots of things. Now I'm going to draw 30 degrees and mark it. And I'm going to mark it in a slightly different color pen. On the camera, that doesn't show up nicely, but in the scanning, it'll show up better. Do you remember, I also once told you this, that if you wanted to draw something that was about 30 degrees, you go over 7 boxes. 1, 2, 3, 4, 5, 6, 7, and up 4 boxes. And I told you that that was about 30 degrees. This is just if you want to make a cool drawing. Now, it's not exactly 30 degrees. It's like 1/4 of a degree short. So if you want to draw it exactly 30 degrees, you make this 7 a little bit shorter. But let's just take it for about 30 degrees right now. And that would allow me to draw 30 degrees on here nicely. So I've got 5, 6, 7, up 4. So 30 degrees going to be coming in 3, 4, 5, 6, 7, up 4. 30 degrees going to be coming in like this. Now, as far as anybody understands, that's 30 degrees. You know, it's as good as anybody could draw. You could draw it as good as anybody could draw. But now let's think about what 30 degrees is. 30 degrees and 180 degrees, I could draw 6 of these 30-degree angles. Let's draw another one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 over 4. Here comes another 30 degrees. And this would be 60 degrees, right? And then another 30 degrees would be exactly on 90 degrees. That's not hard to draw. Let's try another one here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. I'm going to rotate my paper so I can draw easier, but I'll put it back to vertical in a second. That would be 120 degrees. Now, I haven't even started yet because I'm going to go crazy on the circle. 3, 6, 7, 4. Yeah, that one's not too straight. Sorry. But that would be 150 degrees. And if I go another 30 degrees, you know that I land on 180. Because in 180 degrees, there's 6 times 30. So that's cutting the pie into 6 pieces. So what is 30 degrees? It must be 1/6 of pi, pi over 6. What does that make 60 degrees? 2/6 pi, but we don't write 2/6, we write reduced, 1/3 pi. 1/3 pi or sorry, 1/6 pi, 2/6 pi. This must be 3/6 pi. But we don't write 3/6 pi. We write 1/2 pi. This must be 4/6 pi. But again, we don't write 4/6. We reduce to say 2 pi over 3. And this one must be 4/6. This must be 5/6 pi. So I'm getting you used to converting. Now let me draw one more angle in here. And that is, you know, the difference between 45 and 30 must be 15. And 15 was one of our famous angles. So let me draw 15 degrees in here. All I got to do is split the 30, right? But I also told you that if you wanted to draw 15 degrees really nicely, did I say, I forgot what I said, that it was 4 by 14 boxes? No. Does anybody remember? It was 4 boxes tall. And how many boxes over? I want to say 14, but I don't remember it. Well, we'll go study it later, but I'm just going to split the 30 right here. If anybody remembers, shout it out. Now I have 15 degrees. Convert 15 degrees into radians. It's half of pi over 6. What's half of pi over 6? Pi over 12. I'll split this up right here. And this must be 15 past 60, which is 75 degrees. But how many twelfths is that? 1/12, 2/12, 3/12, 4/12, 5/12. And then 90 is a full 6/12. That makes sense. This must be 5 pi over 12. Split this up right here. 6 pi over 12, 7 pi over 12. Must be at 90 degrees plus 15 degrees, 105 degrees. And then the last one I'll split up right here. 15 degrees shy of 180 or 15 degrees past 150. Either way you say it, 165 degrees. How many twelfths is it? Well, here's a full 12 twelfths. So I'm 1/12 short of 12 twelfths. I must be at 11 pi over 12. Now I just did that for the full. You're saying 4 by 16. I think, did I say 4 by 15? Now you're counting it right here. You can try it. I'm going to go back because I don't want to give you a wrong thing, but we drew a decent 15 degrees here. Most important thing is I get you to think in slices of pizza. Now these are thin, cheap slices of pizza. I don't think if you order, by the way, when you order a pizza, how many slices do you get? Let's say you order a round pizza. Now I like Jat's pizza. I like the square deep dish pizza, right? Okay, but when you order a round piece of pizza, how many pieces do you normally get? I'm just curious because you have to think about it. They cut it, they cut it, they cut it, they cut it. I don't think they give you 8. Do they give you 12? Good, Austin, you're doing it. Now, that's why run tan of 4 over 15, and I bet you get really close to 15 degrees. Austin's doing some calculations in the chat window just to see how many boxes. Run tan 4 over 15 for me, Austin. See, that's darn close to 15 degrees. So I think, so thank you for investigating that. I think that that's a good 15-degree drawing right there. Not exact, but darn good. This is about 15 degrees. And you can remember it, 4 boxes over 15 boxes. Okay, anyway, I think when you order a piece of pizza, what do you usually get? I think they take every 90 degrees and chop it into a piece. This looks more like a piece of pizza to me. Now, they don't make it exactly that way, right? But that would make every piece of pizza 30 degrees. Does anybody work at a pizza place? Can you help me out here? Is that what they do is you get 12 pieces of pizza? I'm trying to think. When I order pizza and the kids are grabbing this many pieces and I'm grabbing this many pieces. I think 12 pieces of pizza is how it usually comes. Okay, so, and they don't cut it perfectly evenly, but think about that. A piece of pizza is about 30 degrees. And so a piece of pizza that's 15 degrees, you feel cheated, or you'd grab two, right? I just want you to be able to go from one to the other very simply. But here's how you really do it. The best way to convert, and it's on our formula sheet, is just to think about pi equaling 180. So if you had 60 degrees and you multiplied by pi over 180 degrees, you would convert from degrees to radians. If you multiply by pi over 180, you go from degrees to radians. Now, you do that, 60 to 180 is 1 to 3. So that's how you should remember that 60 degrees is pi over 3 radians. You can remember by thinking about a pizza, or you can remember by thinking this formula. You convert degrees to radians by multiplying by pi over 180. You do the other way. Let's do 11 pi over 12, and that's in radians. Let's convert it to degrees. You convert to degrees by multiplying by 180 over pi. And that eliminates the pi, cancel, cancel, and take your calculator, 11 over 12 times 180. You can pull up your calculator, or you could do this by hand, because 12 goes into 180 exactly 15 times. There's 12 15-degree pizza pieces in 180 degrees. So what you get here is 11 times 15, you get 165 degrees. So if you want to convert from radians to degrees, you multiply by pi, 180 over pi. Radians to degrees. Now, it's time for me to bring in the calculator just to show you what this is doing. And by the way, we are doing what we promised we're going to do today. We're learning how to convert and know the famous angles. I didn't think I was going to get all the way down the page, and I'm not going to. But I want to show you that you make sure you know what radian mode and degree mode is on your calculator. So let me pull up one of my calculators here. Let me toss my book on here to erase it, my newly discovered toy for making the screen closer to you. And let's try 60 times pi divided by 180. And the problem is, you notice the calculator doesn't answer in the terms of the pi. The calculator converts pi to 3.1415926535889, etc. But I could check. I'm saying this should be pi over 3. I could check if it's pi over 3. Pi divided by 3. Oops, Sorry, I got to divide. Okay, it is pi divided by 3. Or let's take 11 pi divided by 12, and let's convert it to degrees by multiplying by 180 divided by pi. I just put things in parentheses to be neat. And calculator says 165 degrees. So you can convert from one to the other just by multiplying by pi over 180 or 180 over pi. And if you forget, just think, if I'm going from radians to degrees, I want to kill a pi. I want to get rid of that pi. If I'm going from degrees to radians, I want to introduce a pi. I want to bring in the pi. But this on your calculator, let's check this out, mode. Second row, second button called mode. I'm probably showing you the screen once or twice because I was afraid I wasn't in degree mode. But now I want you to see you can be in degree mode or you can be in radian mode. Now let's check it out. What is the sine of 60 degrees? I'm in degree mode right now. Sine of 60 degrees, some crazy number. Now let's go to radian mode. And 60 degrees is what in radians? 60 degrees is 1/3 of 180, which makes it 1/3 of pi. So I'm going to go to mode. I'm going to move to radian mode just to practice. And then I'll say sine of what? Pi over 3. And I better get the same number. Yes, I do. So your calculator can think in degrees. Your calculator can think in radians. You're going to get the right answer as long as when you want to talk radians, you got to be in radian mode. And when you want to talk degrees, you better be in degree mode. I was in degree mode a second ago. Which way should you leave it? I always get confused if I leave the calculator in radian mode because I think, you know, I guess most people naturally think in degrees. I think in degrees mostly. So when I'm done goofing around, I usually try to remember to leave the calculator in degree mode. But if you're getting crazy answers that aren't working, say, am I in radian mode or degree mode? That's the first thing you should check. In fact, in some ways, before you enter something, you should check what mode you're in so that you're confident that you're doing this right. Let me clear that screen. Let me go back to this picture. Now, that handout I showed you, called the unit circle handout, makes a tiny bit more sense. That handout I showed you with lots of pieces of pizza, that was, I'll switch to it right now in our last few minutes. That was this drawing that I was making, except I just made it on a piece of paper, printed on a piece of paper. And now that we're going to get into it, we can calculate sine and cosine all the way around the circle, degrees or radians, just by remembering these famous triangles. For example, 60 degrees. The name of this point up here is over 1/2 up root 3 over 2. What do you want to bet? That number on my calculator, sorry, I'll go back to my calculator. What do you want to bet that number on my calculator is root 3 over 2? Yes, it is. Now, let's be careful about what we're saying. I will never say two numbers are equal just because the calculator says the digits are the same. because the numbers go on forever and off the screen. And if I count correctly, what is this? 4, 8. I see 10 digits here. Calculator keeps another 3 off the screen. So the calculator goes out to 13 digits, and usually that's good enough for anything we need. I am not saying that root 3 over 2 is the same as sine of 60 degrees because the calculator told me so. I'm saying that root 3 over 2 is the sine of 60 degrees because I learned that if this radius was 1, the short side is half of the radius, and the long side is root 3 times the short side. I learned that famous triangle, and that's why the name of this point is over 1/2 up root 3 over 2. And that's how I labeled it on this handy sheet that I wanted you to have. Over 1/2 up root 3 over 2. Okay, we're going to call it quits, but I just want to make you equally good at radians or degrees. You can speak French, you can speak German, you can speak Spanish. I don't do very well in other languages. When I was in high school, I took a lot of Spanish, and I probably used it, but I haven't used it lately. I grew up in Southern California, so I used it. Summer jobs, restaurants, stuff like that. I know a little bit of German, not enough German that I wouldn't die if you dropped me in Germany. I could know where the food was. I could know where the restroom was. I could know where the hotel was. But I don't speak another language. Oh, that's very good. I'll mention that. Yes. But I want you to speak degrees, and I want you to speak radians. I want you to be fluent in degrees or radians. That is what you have to do. Now, mils of a circle ever going to come up in trig? That is very interesting. So I've shown you how to measure a circle in degrees. I've shown you how to measure a circle in radians. Are there other ways to measure a circle? There are many other ways to measure a circle. Sometimes people get totally bugged by a right angle being 90 degrees. So they cut every right angle into 100 degrees, and they call a full circle 400 gradians. Austin measures things in mils. Tell me, where are you doing that? It's like a machine shop or a CNC machine, Austin? There are many, many ways to measure a circle. And just the ones that are going to be useful to us are degrees and radians. I am not going to teach you gradians. I'll admit I haven't heard of a mil before, but I'm going to go look it up. Oh, okay, you're thinking it's firing solutions. Very good. Okay. Where else would you use angles when you want to measure something precisely? If you're doing firing solutions in artillery, Napoleon began employing mathematicians way back in the 1800s to measure trajectory of cannonballs. And likewise, there's many, many things if you're looking at a firing solution of an artillery or something like that, because you got to consider lots of things, wind, range, things like that. But I did not know that terminology. Thank you. I'm going to go look it up. Okay. I won't make you responsible for every different way people measure circles. You're only responsible for degrees and radians. Now, this is a great start. You can dig into the sections that we're doing this week, and we'll mop it up on Wednesday. But if you have a question, send me the question. I'm going to pop out of this browser. I'm going to go read up on exactly what a mill is, and I'm going to post this stuff online so you can look at it later. So thank you very much, and I'll see you on Wednesday.